So far in 6.1 we talked about what? We talked about standard normal distribution, which is a normal distribution that has a mean of Santos, mean of 0 with a standard deviation of 1, right? So this is, so as far as we know, we were able to use or the table and such in a situation like this, right? Okay. So let's go to page 243. We're on 6.2. We're going to do actually the real applications of normal distribution. So let's go to 243. Do example number 1. Heights of men are normally distributed with a mean of 68.6 and a standard deviation of 2.8. So we have a u of 68.6 and a standard deviation of 2.8. And we want to know the percentage of men who are taller than 72 inches. So we have 68.6, 2.8, and we want to know who is taller than 72. Correct? This is what we're trying to find. Okay. So what's the first thing that we need to do? We need to find the z-score. Very good. We need to find the z-score, right? And that's going to tell me. So I need to find the z-score, right? So the z-score. Anybody remember how to find the z-score? It is the actual value, x, right? 72.
X minus mu. X minus
mu divided by
2.8.
2.8. So really, again, if you look at the definition, of the z-score. The z-score is how many standard deviations away am I from the mean, right? This is how far away I am from the mean, and I'm going to divide that by standard deviations. I want to know how many standard deviations I am away, right? So what would it be? What is it? 1.214. Okay, so what I want to know is this guy, right? If I were to use the table, how am I going to find this guy? Let's go to the table. The table is what, 601, 602 or something like that or whatever? What was it? 680 something? Oh, here you go. 684. If I go to 684. So I have a positive z-score of 1.214. If I go to 1.214, am I at 1.21? We'll just read off 1.21. What do I get?
0.8869.
Everybody see that? 0.8869. We're able to put your finger on that number?
Yes.
0.8869. So what is that? In my graph. The area of what? Right here? Is that area that we're looking for?
No, the area in between.
It's the area from down this way. 0.8869. So the area here would be 1 minus 0.8869. You see that? Because the entire thing is 1, right? And they're telling us here to here is 0.8869, correct? So this guy here is going to be 0.1131. Okay, 0.1131. So let's see if that is correct. And yes, 0.88 or 1139. 1131, I'm sorry, 1131. Okay. How would I verify this with my calculator? What number would I use? So I would do, am I doing inverse norm or am I doing norm CDF?
CDF? Normal?
I'm doing norm CDF, right? So norm CDF I'm going from z-score of this, right? 1.214 to, I don't know, we'll just call it 100, the upper level, right? Some arbitrary number that's way out there, right? 100 meaning not 68, 72, 100, but 0, 1.214, 100, that 100. In other words, 100 standard deviations out. Ever see the difference there? Okay. And then I would put 0 and 1. Will you run the numbers for me?
I got 0.1123.
What?
It's
Point
1123.
1123.
23. Yeah.
1123.
24.
24, you can be rounded up.
124.
Maybe you could do 5.
Okay, we're going to call this close enough. Or we're going to call this close enough. It worked. Okay? So again, what was the procedure? What are the steps that we went through? We first found the z-score, and then we put it into the, if we're going to use the calculator, we just put it into my norm CDF in a standard normal distribution, correct? I did that. So we had to find the z-score and then put it in, correct? So there was that intermediate step of finding the z-score that we have to do, right? Especially if we're going to use the table, right? In order to use the table, you have to find the z-score, because that's all that table is the z-score, right? But if you're using the calculator, I just go ahead and plug it in and I'm going to go like this, okay? Take your calculators and go ahead and put in this, see if this works. I want to find, let's compare this.
Oh, no.
Whoops, I'm sorry.
We're chilling. We're probably dead.
Lower level of 72,
We can maybe.
upper level of 110, just, something out here. And then my mean here is 68.6 with a standard deviation of 2.8.
Oh, what is that?
1123.
Oh, what does that mean?
You don't need to do
You
it.
don't need to find
I
it.
do not need to find the z-score. If I'm using the calculator, I can get rid of that intermediate step altogether. Okay, I can go straight from here and say, okay, 72, upper level is way out here, 110. That's my mean, that's my standard deviation.
But
One
why-
step.
Why 110?
Why 110? Well, I can put
You know, it's just
1100 if you want. It doesn't matter. Something that's just way out there, right? Okay? It's just an arbitrary number. I don't want to put 74 here, right? That's too close. But I want something that's kind of out there, right? Okay, all right. Okay, so this is the real application. This is how we use the norm CDF. And this is the power of the normal distribution. Okay? You give this, and I know the rest. The calculator's going to calculate it out. I know everything. Okay? Example 1 was example number 1. Let's do example number 2. In example number 2, we have U.S. Air Force requires that pilots have heights between 64 and 77 inches. Heights of women are normally distributed from 63.7 and a standard deviation of 2.9. Based on that, what percentage of women meet the height requirement? Okay, so the height of the women are what? It's normally distributed at 63.7, right, with a standard deviation of 2.9?
Yeah.
2.9. Okay, I want to know what percent of women are between 64 and 77, right? So obviously I'm going to use this guy. What's my lower level? Lower limit?
64.
64. Upper limit?
77.
77 with a mean of, with a standard deviation of
2.9.
What do we get?
0.4588.
0.4588.
Yeah.
Okay, 0.4588.
You take
Okay.
it.
So, through where we at? The book says when they did it using the back of the book, they got 0.4601. 4601. Okay, that's close enough. We're good. Okay, we're good with that. Flip the page. Example number 3. When designing equipment, one common criterion is to use a design that accommodates 95% of the population. Ooh, here's that 95% thing again. That's kind of like the 5%, right? The statistically significant 5%. Remember that? Okay. Example 2, we saw that only 46% of the women satisfy the height requirements. 45.88 for us. Okay. What would be the maximum acceptable height of a woman if the requirements were changed to allow the shortest women to be pilots? Okay, so what are we looking at here? You want 95%, correct? So I need to find the z-score, the critical z associated with 95%, right? So, and we found that yesterday. Do you remember seeing that yesterday? Go back to that table, go back to table, your table, your appendix, where is it at? Here we go. 6, one of them just used. 685. And we're trying to read off 0.95. Where do I read 0.95 off of? 1.645. Everybody see that? You see in the positive part, it's 1.645. Okay, the book reads 1.645, okay, which is good. So we're good there. So we need to find out what that is, correct? So we would be what? I know that this number here, now we're not doing this anymore. We're looking for a z-score here of 1.645. So how would I back the actual number out here? Z-score is, I don't know what this actual number is. When I subtract it from the mean and divide it by the standard deviation, right? Because that's what the z-score means. This means that I am this many standard deviations away from the mean, right? So I'm backing that out. How do I find x?
Get it by itself.
I would multiply both sides by 2.9, right? And I would move this guy over, right? So I have to add, so it would be 2.9 times 1.645, add 63.7 on both sides, and that would be my answer. Everybody see that? Okay. And if I do that, I would end up with a 68.4705. 68.4705. How would I verify this? No, I can just put it in here, right? I should just put it in here. I can go my lower level of somewhere over here, right? 20 sounds like a good number. To 68.4705 with a mean of that with a standard deviation of 2.9. Somebody run those numbers for me. .95. That's what I'm supposed to get, right? 95%, right? 0.95. Okay. All right. Everybody feel comfortable with this? Everybody feeling this is basically, again, the real life applications. Okay, are we good?
Yeah.
We good? All right.